We are in business now. Any questions? So I tried to give you a hint last time about the confusion here. Let me just repeat that message again. If you think you are accounting for all the bonds that are bearing load, then each bond occupies an area of S, and therefore the density is 1 over S, and therefore you would estimate your stress, theoretically, the limit is 3 nanonewton divided by the area, which is about 0.18 nanometer squared for polyethylene. So you get 17. But we see, disappointingly, 17 only showed a stress level of 170 megapascals. I just make it up so it's the same, which means it's smaller by a factor of 100. Okay? That's clear. And therefore, it was concluded in However's book that, it must not be a matter of sensation, because sensation will produce much higher stress. Right? That's what you read there. And so where does this factor of 100 come from? Or rather, what's wrong with his induction? But there is no chain breaking. Well, what's wrong is very clear. He's assuming every bond that's coming to go through your surface is bearing load. Yeah, that's by definition. And we know simply that's not true. Because you just have a coil. You don't have chopsticks lined up. I give you this. Okay? Hear it. So that's where it's wrong. The rest is irrelevant, whether you have sensation or not. Okay? So the guessing game we made was to think, perhaps the load-bearing strength times some magic force. In my calculation, I tried, perhaps that load-bearing strength is just 1/10 of that. Remember, in our analysis, the ratio of load-bearing strength versus phi is exactly the cone length versus load-bearing strand length. As I admitted last time, we don't know what that number is for load-bearing strand because it involves multiple chains, and they have to find each other to have a hook. So we don't know. But we do know that this is also proportional to cone length for all polymers. This is where universality comes from, because we're talking about cone length, so we don't care about polyethylene versus polybutadiene or PVC. And so the hope was that this is another. So maybe I should, bragging a little bit more, maybe I should call my model whatever model. Because this is if you recall, this is a bit like the packing conjecture. We say something was constant, right? You need to reach 6 for all polymers. Here's the same thing. by our analysis, this ratio is constant. It's pretty powerful. And the fact we had, try to move this away. The fact we had this indeed linearly proportional to each other indicated indeed that this density is more or less constant for all polymers, and which means this is more or less constant because, as I said, the cone length is almost constant for all polymers. So the rough logic is that we understand why this could be linearly changing. So let me just indicate when you encounter something like 100, don't wave your hands. Don't just brush it away. Says that's, who knows? Maybe this is only 100th. Sorry, it's only 100th of the phi. In that case, it will be all chain breaking. You see the point, right? By definition. But man, a factor of 100 is a lot. Okay? So indeed, for you to claim that your network is as dilute as 100, you know what it means. Okay? You know what it means. Let me give you an impression of it. Gosh, can I give you an impression of it? It's like you have 100 dots. Oh my God, I'm going to run out of time, right? You have 100 dots, okay? And only one of them was effectively bearing the load. Is that reasonable? Well, until we have a calculation of this, we don't know. But I think it's unreasonable. Moreover, as I said in chapter 12 of Connie Ross's book on polymer glasses. Sorry, polymer glasses. It's a book published in 2016 or so. I have a chapter 12 arguing about why it is not chain scission, the brittle failure. Okay, so do you understand the mistake here about the conclusion? In other words, they find that there is a theoretical difference. I'm flipping another page just to indicate this lack of understanding is universal. This lack of understanding is universal. This is a much more recent book by an authority in the field who is saying identical things. He's saying that it's dramatic. It's saying the same thing. That because of the factor of 100 difference, he's using the same data. In fact, this is the plot from his book. Because of the difference of 100, he's claiming, if there's any breaking, it will be less than 1%. Missing the point, or made the wrong assumption that all bond would be load bearing. So there's no concept of a load bearing network in this consideration. Okay? Whereas we're asking why there's this discrepancy of 100 times. Yeah? Because we observe the strength of our polymer that's only 1/100th of this theoretical limit, which you just pointed out about the mistake of that estimate because you assumed every bond bear load. Bear load as much as breaking that bond. So why we have 150? Meaning, what does that mean we have 150? Well, we had some notation there, but it's okay. And I'm not asking you to, you see, you cannot criticize anyone if you don't understand what he's doing. So first you have to understand what I'm doing. Yeah, there will be a stress we measure that presumably come out of the load-bearing strength. But we know this a factor of 100 smaller than the theoretical limit. So it could come, remember the theoretical limit is this. So it could only, in the simple picture, it could only come from either of these two factors. I know you're trying to phrase it. So what are we saying actually? Or both? It's both. So we're basically saying this is weaker by a factor of 10. This is probably smaller by a factor of 10. That's it. Right or wrong? That's a different story. At least you understand what I'm saying. I'm pretty happy with it. That's all I can say. In other words, the task, of course, is to see. This is the problem. The problem is just too difficult. But at least we're getting somewhere with this, right? So this is. You see how elementary can you be? We're talking about strength of your polymer, your dear polymer. This is the only reason I'm bringing this up, because there's nothing more elementary than this. Than the strength of your polymer. Than the strength of your hydrogen. As if it's not complicated enough. We are going to, I recall it was 2B. A part 2 of mechanics of solid polymer. As if it's not complicated, what we had. Well, I assure you, what you are dealing with so far was indeed less complicated, because you just have a random coil, you freeze it up, it becomes glassy, and that's all there is. Now comes crystallinity, crystallization. And so the first thing one could indicate, again, it's a matter of what to do first. You always do the simplest one first, of course. In your research, you do the same. And you will find what we learned about polymer glasses will ultimately serve you very well when you deal with semi-crystalline polymers, because there are two classes of semi-crystalline polymers. In particular, there is it's my classification. I venture to say they must existed before in the literature. I'm just too lazy to bother checking out who was the priorities, who did it. But to me, there are two classes. The second class is the one, its Tg is higher than room temperature. Because I'm eager to connect with what you just learned. Okay? I'm eager to do that. Which means what? At room temperature, it's glassy. It's glassy in what sense? It's glassy in addition to crystallization. Examples you can have is very, very well studied polylactic acid, we call it PLA. Examples you can have, turns out we normally avoid crystallization of PET, which has a Tg of 60, this has a Tg of 70. So it's glassy. There are a few more. We looked at one that's EVA, ethylene vinyl alcohol. It has something around 50, 55. They're glassy. Can be glassy. And of course, when you speak about semi-crystalline polymers, typically what comes to your mind is polyethylene, polypropylene. But watch. Your I indicate that in a beginning class, in the first class actually. Your polypropylene in freezer belongs to class B. Does that make sense to you? Because your polypropylene's Tg is about -5 to 10. -10. Something in that neighborhood. So your polypropylene is also class 2 if you are willing to think about using it below -20 in Canada. Which you put, polypropylene is widely used in the car. So go to Canada, you will have to deal with it. And just to spike your interest, polypropylene, once they belong to class B, is brittle, which I indicated in the very first class, if you still recall, with the contaminant. Man, we have to deal with that. Okay? Now, the other side of the whole story is my bitter complaint about why we have not advanced much more in the subject. You know why? You can blame for your good luck. Polyethylene, polypropylene, if you use both of them above Tg, above room temperature, at room temperature, they're damn good. So, just like, sorry to say this, it's just like if I'm in poverty, you don't know what in poverty means if you are not. So once we have such good polymers, we got spoiled. We don't know what the bad polymer is about, why they are bad. Meaning, well, I'll talk about mechanics only, right? Why they're bad. So, again, several hundred billion pounds of polymers, they are either glassy or semi-crystalline or rubbery, which we use in tires. That's about, that's a, if anything, there should be a part C, which is rubber or cross-linked rubber, and maybe even thermosets. And this is the part we absolutely run out of time, and I absolutely don't have enough expertise either to deal with. So that's the three type of solid polymers, if you like to be thorough about it. The first type is glassy. Enough. Life is short. Enough to deal with what we can deal with, and before you run out of time. So let's talk about this semi-crystalline polymer. And ask why polyethylene and polypropylene is good. Well, you have a cheap answer first.